I picked out an OPAmp problem to work on, just to give me a chance to go over it with you. So the OPAmp symbol here, we usually draw at a minimum 3 connections. The inverting at the minus, the non-inverting, and the output. So those 3 voltages, those node voltages. And there are 2 other connections that we don't always mark, but we sort of assume that they're there. So in this one, they do have a ground for one of the inputs. So that's replacing either the positive or negative voltage supply. And they don't even draw the other one, but we assume it's there. All right, so we can safely assume that there's a voltage supplying the internal workings of the OPAmp chip. All right. For our purposes, we're using the ideal model, where if we mark these 2 voltages, the inverting we'll call V minus, and the non-inverting V plus, and the output is V out here. And then the current associated with each of those, and my drawing's not really big enough, the current there, I plus and I minus, we assume by our model that those are equal to 0. But the current coming out can be whatever it needs to be. And that's because of that other source that we're not even drawing. That source is providing power that's producing this output current. So on the input side, we've assumed that there's a very high resistance here at the input, which prevents any current from flowing in. And because there's no current between these 2 nodes, we assume that they have no voltage difference. If we were to subtract one from the other, we would get 0. So we can either say the difference is 0 or the 2 inputs are equal to each other. So if we can figure out one of them, we automatically know the other one. Right? And then we can't really go around any loops and do KVL, so we can't do mesh on a OPAmp problem. So we always do nodal analysis at whatever nodes we have and whatever places we need to figure out. So our plan is always going to be nodal analysis.